So, hi everyone. Thanks for inviting me here. It's my pleasure to share my recent work. I'm Wenhao, a PhD student in chemical engineering at MIT. So today the topic I want to talk about is molecular synthesizability and synthetic tree generation for synthesizable molecular design. And this topic covers two papers of mine that I listed here. So molecular design is the problem I'm interested in, which is a fundamental problem in chemical science and engineering. And as we know, the structure of the molecule fully determines its property. So discovery of any functional molecules require designing the molecular structure. And here is one wonderful example of how each component of the structure contribute to the property of imatinib, tyrosine kinase inhibitor. And of course, not only for pharmaceutical application, but discovery of novel functional material is also important application of molecular design methods that could potentially address many grand challenges faced by human society, such as organic solar photocell for clean energy. And formally, the problem of molecular design could be formulated as an optimization problem. So we are looking for some molecule M to optimize some desired property F of M, such as redox potential for battery design or inhibition against the disease target for drug design. And the search space is a set of available compounds called chemical space. And in the history of computational chemistry, people focus more on the QSPR problem, so quantitative structure property relationship, which is about given the molecule M to infer the property F of M from it. And the molecular design is the inverse problem of that, assuming already have access to F of M to search for an optimal M. And currently, systematic approaches, which I mean, unlike the rational design that are restricted by a case or a subdomain, can be generally categorized into two classes: screening and de novo design. So screening is basically just an exhaustive search that to enumerate and evaluate every candidate. And the defects are obvious, very time and resource consuming. And we can still only screen a tiny fraction of the whole chemical space. And de novo design is to construct the molecule from scratch and aim to find the optimum more efficiently. That's ideally de novo design, if it works, is more preferable than screening. And here is one recent successful application of de novo design methods in drug discovery. So in this work, a team from in silico medicine developed a deep learning-based algorithm called GENTO that successfully identified an inhibitor that exhibits in vitro bioactivity against DDR1 kinase. Though this work is a little bit controversial, they did discover this drug candidates within a month and a half, where the process usually takes years. However, that doesn't mean we are already here. Indeed, the team of in silico medicine, they manually selected only 6 molecules from the 40 based on synthetic accessibility. And that 40 is already filtered from a list of 30,000 initially generated. And the problem is not a single case. Indeed, most de novo design algorithms exhibit poor synthesizability, which impedes further experimental validation. So before the deep learning era, only single digits of de novo design molecules have been experimentally validated each year. And cases are probably even worse after the boom of deep learning, because in recent years we see a lot of new models being proposed, but very few of them proceeded to experimental validation. And here is a recent tweet from a researcher in the field, and we can see it features the problem. And yeah, it is nature to think about approaching synthesizability problem as a multi-objective optimization. However, I will show it's not that easy. Synthesizability, by definition, is the easiness of the chemist to synthesize a molecule. So to some extent, it's an intuitive and subjective concept. So different chemists may feel differently about the same molecule. And because chemical reactions have residual selectivity, so even changing the position of a functional group, like here from this position to this position, or just an atom in a position in a ring, can largely affect the hardness of the synthesis. So though the overall structures are very similar, so that the traditional simple heuristics cannot distinguish them, that the synthesizability differs a lot. So this we call it high nonlinearity, make the simple heuristic or machine learning scores very difficult to capture the subtlety. And it is also sensitive to chemical availability. So a very complicated structure may be easily obtained from a reaction with a natural product as a precursor. And formal attempts include three classes. First is cross-site scoring, which is just let have a group of experts to score the molecule, because it is intuitive and subjective concept. And the second is based on the structure complexity, such as SA score, widely used. That so SA score just use the substructures frequency of occurrence as measurements of synthetic accessibility. And the third class is based on synthetic pathway, like SA score, which is a deep learning method that trained to distinguish if a molecule is more tend to be reactant or product. And for the reactants, because they require fewer reaction steps, so we think they are easier to synthesize, which is a chemical intuition. And among the three, the most convincing metric is still the direct scoring by a group of experimental experts. And indeed, the expert scores are usually used as the ground truths to compare, such as in this figure from the SA score paper, or to train other machine learning models. But of course, to have a group of experts that is large enough to reach a non-biased value, it's labor intensive, and it is also hard to replicate and not scalable. So let's recall how chemists figure out how to synthesize a molecule, and the methodology is called retrosynthetic analysis. And the process, if done computationally, it's called computer-aided synthesis planning, CASP. So the modern CASP tools, such as our group's implementation called ASKCOS, typically rely on Monte Carlo tree search process that from a target compound, in each step, in each iteration, we feed the target into a neural network to obtain the potential precursor. And for each precursor, we use another model to check if it's a feasible reaction or not, and filter out the unfeasible ones. Then we check the obtained reactants are viable or not. If not, then we repeat this process and continue to grow the branch. If yes, then we have a synthetic route to the target product. So that's a CASP tool. So the question is, could a CASP tool serve as an artificial chemist to evaluate the synthesizability score as an alternative to the expert scoring? And to be short, the answer is yes. The detail is in our first paper. We found that the result of ASKCOS is compatible with our intuition. So it does capture the nonlinearity of the synthetic accessibility. So it can find a pathway for this, but cannot find even a path for this molecule. And besides, compared to simple scores, it actually provides an actionable synthetic pathway. So to some extent, it provides the interpretability of the synthetic accessibility. And unlike human chemists, a ASKCOS can be accessed unlimitedly. So, but it is time consuming. Retrosynthetic analysis for one molecule typically takes about 1 minute. That's already faster than the earlier ASKCOS, but that's pretty expensive as an oracle or a filter in the molecular design. So based on ASKCOS, we evaluated the de novo design methods in Guacamole. And here, the base from data represents the virtual screening from Campbell as a baseline. And the color represents the synthesizable fraction of top 100 suggestions. We run experiments for 10 different objective functions in Guacamole to simulate the process of drug discovery. And we can see all of the methods have a pretty high risk of proposing unsynthesizable chemicals. And the results vary according to different properties, but most of them, all of them are significantly worse than the virtual screening baseline. And in some cases, we can see that there is even no synthesizable molecules found in the top 100 suggestions, which implies post hoc filtering after normal de novo design algorithm may not be a good strategy.
I have one question.
Sure.
Why do some properties kind of give a higher number of chemically accessible molecule and others can give kind of a really lower number? Do you have a rationale behind that?
I think that's because I think the landscape of those some of the objective functions probably matches some to some extent matches the landscape of the synthetic accessibility, if that's a score. So some of them are like some machine learning models, especially they extrapolate poorly. So after when it comes to some molecules that beyond like normal training set, it may predict a very high score for them. But indeed, the structure is very weird. So in that case, it has alignment between those two properties. So yeah.
So your hypothesis then, if we increase maybe the training set on which some of those generative method has been trained, then we might be able to increase the accessibility of some of this, but only to some extent, because like there's still be some part of this of the molecule that will be outside of the synthetical, the accessible molecular space. Is that clear?
I'm sorry, can you say it again?
Yeah, so is your hypothesis that if we increase the size of the training set, then we will increase the percentage of molecules that are easily accessible?
Sorry, not really. I think so. So the chemical space is indeed unlimited, and we cannot like test the like the property of the unstable molecules. Like I will show some examples later, but yeah, if there's a lot of like unrealistic molecules that may not even exist in nature, so we will never have properties or like at least experimental properties for them. So I think there will always be a problem of extrapolation if we use a machine learning model as an oracle.
Okay, thank you.
Yeah, but of course, if you enlarge the size of the training set, yeah, I think in general, it improves the quality of the oracle, definitely. Yeah. So, yes, is there a better approach? And from above, we know what we know is the best way to ensure the synthesizability of a molecule is explicitly finding a synthetic pathway for them. And so why not directly design the synthetic path instead of design the molecular structure? And a valid synthetic path to a target molecule, like what I'm showing here, can be abstracted as a tree structure, where all of the leaf nodes should be viable building blocks that are available in the chemical market. And the root node is the product molecule. And each link between the nodes should represent a valid chemical reaction. Further, as we know, the task of CASP synthesis planning is also to find a synthetic path for a target molecule. So these two tasks could be solved within one shared task of synthetic tree generation using algorithms like we did to the molecular graphs. So within this framework, synthesis planning is to generate synthetic trees whose product molecule matches the target molecule. And the synthesizable molecular design becomes to optimize the property of interest of the product molecule with respect to the structure of a synthetic tree. And we need to mention that this idea, of course, is not novel. Especially the synthesis-based molecular design has a pretty long history, but the majority of them, especially recent work, cannot cover the whole space of synthetic pathway, like molecule chef or PGFS. And among the recent deep learning-based methods, only John Brashaw's DOG models could generate convergent synthesis paths. By convergent, I mean, like I'm showing here, there are two sub-branches could join together. Convergent. So we will just talk about the DOG, discuss DOG here. So what is still lacking from DOG? We think there are two major flaws currently with the DOG. First, DOG model rely on forward reaction predictor. But all of those machine learning reaction predictor suffer from bias of positive reaction data that is caused by the custom that people only successful reactions could be published. And so people just throw away those unsuccessful reaction data. And so it cannot be easily solved. And second is also because they are using the reaction predictor, they don't explicitly use the molecular structure of the intermediate products as the input information. So within their generation, after they choosing the reactant, they just predict the action to code the reaction predictor as a black box function, and then proceed to select the next action step. So the model, the RNN model, kind of have to learn to approximate the reaction prediction outcome, so which is inherently unnecessary and challenging. And for synthesis planning, very few have tried that. John Brashaw's DOG has one of them, and their model called retro DOG. But unfortunately, in their paper, they only showed 3 unrecovered cases. And yeah, as far as I know, there's no successful synthesis planning that doesn't rely on tree search process before. So to improve from that, we formulate the generation of synthesis trees as a Markov decision process. To explicitly use the intermediate product structure, we define the state as root molecules of the intermediate trees. And because as long as we obtain that intermediate, how we obtained that intermediate doesn't affect the further planning. So it exhibits a Markov property. And we enforce depth first order for generation. So that's at most 2 subtrees can occur simultaneously, which leads to at most 2 root molecules can occur. And the order of the expansions always takes place from the most recent one, so which introduce the order between the two root molecules. And we define each reaction step as an action step in this MVP, and define 4 types of actions. So using this tree as an example, from an empty set, we first need to conduct an add action to sample a new viable building block from a list of given viable building blocks, and apply a reaction, a unimolecular reaction, to obtain a product. And an expand action that takes the most recent intermediate as reactant and conduct a reaction, here a bimolecular one. And add reaction again, bimolecular reaction, and expand action with a unimolecular reaction. And then a merge action could take the 2 intermediate as reactants and conduct a bimolecular reaction. And in this way, it allows the generation of a convergent synthetic pathway. And till the end, after all, the end action means to finish the generation and output the tree. So to ensure the validity of the synthetic tree, we also need to make sure each step is an actionable chemical reaction. So currently we have 2 choices. First is machine learning reaction predictor, and domain-specific reaction rules encoded as reaction templates. So such as what I'm showing here, those 2 examples, one unimolecular reaction and one bimolecular reaction, all encoded in smarts, reaction smarts. So of course, based on the discussion before, we choose reaction templates. And so the transition dynamic would be, we just reject all reactions that don't follow a non-template. And lastly, although we will not use it in our model training, but reward could be naturally defined by the purpose of the task. So for synthesis planning, it could be defined as the similarity between the product and target molecule. And for design, of course, it's just the property of the interest of the product molecule. So to given that MTB formulation, rather than a traditional reinforcement learning approach that involves explicitly searching process, we formulate the synthesis planning as a probabilistic generative modeling of synthetic trees conditioned on a target molecule, so that we can amortize the searching cost with the training cost. And we use offline data to train a policy network. And within each step, we sample an action, which is a set of 4 components we will introduce in detail later. And from the policy network, using the current state and the target molecule as the input, and apply this reaction to the environment to grow the synthetic tree. And we will take the synthetic tree and the product molecule as the output. And if the product molecule is identical to the target molecule, then it's a successful synthesis planning, and we call it a recovered. And concretely, we use Morgan fingerprints, which is a graph-based representation of the molecular graph to represent the molecules. And because there will be at most 2 root nodes, and between them there's an order, so we can just concatenate the embedding of them, and with the embedding of a target molecule as conditional code. And this forms the state embedding. And in each action step, we need to sample 4 component, action type, first reactant, reaction template, and the second reactant if the reaction is bimolecular one. And we trained 4 separated networks to predict the 4 components, and all of them takes the state as the input, and some of them takes the previous output as the input as well. The action and the reaction networks are classification networks. But as there are too many viable reactants, the reactant selection networks only predict 256-bit fingerprints and conduct k nearest neighbor search to select the reactant from available building blocks.
We have one question in the chat. So Cass is asking if the reaction template take into account the necessary reaction condition, temperature and pH and those kind of things.
Currently, no. So yeah, it just encodes the transformation from a reactant to a product or a product to reactant.
Okay, and what happens if the reaction template give you kind of two products? How do you continue the synthesis? Do you pick one or you?
I just randomly pick one.
Okay, cool. There's a few other questions in the chat, but related to the previous, to the baseline and everything. So we might ask them at the end of the meeting.
Sure. Covered. So given that previous network, we indeed have a decoder that decodes a moving fingerprint to a synthesizable molecule. So it translates the synthesizable molecular design problem to a more convenient numerical optimization of fingerprint. And we apply a genetic algorithm for to do that. So in a typical setting, we can select a random batch of fingerprints from molecules in the zinc database as the initial pool, and crossover and mutate to obtain the offspring pools, and decode to obtain the molecules, synthesizable molecules, and select based on the desired properties. And the crossover is defined as inheriting about half of bits from one parent and the remaining from another. And the mutation is just defined as the flipping a number of bits with some probability. We iteratively apply this procedure until stop criterion is met. And for data, we manually selected 91 reaction templates from previous publications, comprising 13 unimolecular reaction and 78 bimolecular reactions. And for purchasable compounds, we use enamel building block US stock as a purchasable list of purchasable compounds, about 150K. And synthetic trees are generated by applying random policy to the aforementioned DP. And we filter the synthetic tree by the QED, drug likeliness of the root molecule. And after all, we obtained about 200K synthetic paths for training and about 70K for validation and testing each. And each network is trained as a separate supervised learning problem using a subset of information from the non-synthetic roots. So to validate our model, we first test the amortized synthesis planning, which is the task that ritual dog failed. So we use the test set constructed from our templates and building blocks as reachable data, which means all of the molecules in this set can be constructed within our framework. And random sample from Campbell as unreachable data, which means the molecules in this set cannot necessarily be constructed with our template set and viable compounds. And we use k equals 3 in the nearest neighbor search of the first reactant and k equals 1 for the remaining. Because of the amortized approach, instead of a full tree search, it only takes about 1 second to plan a synthesis pathway for a molecule compared to previously is 1 minute. And so even with that speed, our method could recover about more than half of the reachable target molecule, which shows a promising approach to rapid synthesis planning. And for unreachable ones, we could still reconstruct about 5% of them. We conclude the gap is mainly due to the incompleteness of the reaction and viable reactants. So further, in case of unrecovered, yep.
What, based on those experience, like what would you say the rate of recovery is for the whole chemical space? Do you have any idea? Like in general, let's say you are not limited to those two sets. In general, for any given molecule, would you say that your model is able to recover that or not?
I think the Campbell case could represent that. And if we are talking about a drug-like chemical space, so yeah, a random sample from Campbell may represent that. So I think it's about a 5% rate to recover that molecule.
Okay, and I suppose that this 5% mean that at optimization time, your method will definitely do a bit worse than all the methods that are not restricted to the synthesis criteria, right?
Sorry, can you say that?
I'm asking if this recovery rate actually means that if at optimization time, your method will actually do a bit worse than all the other methods that are not restricted to find the synthesis route.
I think so. So yeah, this is a synthesis planning task. So yeah. So by 5%, I mean it's just pick the 3 nearest neighbor in the first, and then pick the top predicted one in all of the following steps. So it's just like a one-shot generation of the synthetic tree instead of like a tree searching process that we typically applies. So yeah, it's a little bit low percentage of recovery, but yeah, if we have a beam search that enlarge the width of the searching, then we will have a larger recovery rate. Yeah, but more consuming times also. So it's just it will go to in between of the current approach and the traditional tree search approach. I'm not sure if that answers your question. So.
Yeah, thank you.
Thanks. And so further, in the unrecovered cases, we find that the produced molecules are usually structurally similar to the target molecule, and verified by the average similarity, the KL divergence, and the FC distance between the input and output sets. And those are 2 successfully recovered cases for synthesis planning with targets from Campbell. So these are the targets. So these 2 are the most similar molecules that we find in our training set, and both of them only have about 0.3 something similarity, and those are the pathway our model predict. So we can see that our model successfully constructed synthetic paths for them, even didn't see any similar molecules during the training, showing a good generalization ability. And here, what I'm showing is the correlation between some common properties of target molecule and the output molecule. So SA score, log P, molecular weight, and the QED. And in each graph, the x-axis are the properties of the input molecule, and the y-axis the property of the output molecule. So we can see that as long as the structure similarity can lead to similarity in property. So even the unrecovered cases from our model could potentially serve as an synthesizable analog recommendation that suggests the synthesizable analogs with property that close to the input molecule. And here I'm showing two unrecovered cases. So in the first case, although our model cannot reconstruct this target molecule, it gave us a pretty similar structure that have many common substructure to it, while the most similar molecules in the training set differs a lot. And in the second case, the target molecule is indeed a symmetric molecule, and our model kind of constructed like half of it. So although they are not very similar in structure, we think the synthetic roots of this molecule could also could somehow inspire the synthesis of original target. So the output we think is also valuable. And for synthesizable molecular design with genetic algorithm, we first validate our model with some common heuristic oracle functions relevant to drug discovery. So we show top 3 molecules in this table, the values of top 3 molecules in this table. And we find that in terms of optimization ability, our model consistently outperforms GCPN or ModiKN that are 2 reinforcement learning methods, and is in general comparable to GA+D on mass across different tests. So in general, it is comparable to the SOTA performance, but not very strong. But of course, our focus is to design synthesizable molecule. Here, I'm showing the top 1 molecules from the best performing models in the GSK3 beta task. So we can see that even the ones without a chemistry background can see our design, although marginally worse in the value of the GSK compared to other models, is much simpler in structure, and combined with a plausible synthetic path obtained from our model, with just one step of Suzuki reaction as a byproduct, I think our design is more valuable. So even though the values are lower. And this is the result of JNK. And we can see that although this design doesn't seem as good as the previous one, it is still much better than the design from the other models. And in those cases, they still have a very high scoring. So that's the problem I mentioned. Some oracle functions, especially here is a machine learning model, you can never cover those kind of molecules in your training data set, right? And to simulate a more realistic application case and have a more thorough quantification of evaluation of the performance, we also optimized a docking score against 2 important disease targets within the TDC generative benchmark. So dopamine D3 receptor and the main protease of the SARS-CoV-2. And to conduct a fair comparison, we limit the number of oracle codes to 5,000 times. And here is the result of dopamine D3 receptor. Again, the docking score are not as optimized as the most SOTA models, but our model successfully had both high passing rate of the structure quality filter and a low average assay score. 80% of the generated molecule passed the filter, and while others only have 10 or 20% can pass, or even the single digits can pass that filter. And in terms of assay score, we also have a pretty low average score. And all of this implies that our generated molecules have a good structural quality and can be easily synthesized. So not even mention we have a actionable synthetic pathway as a byproduct. And here are some results of the dopamine D3 receptor docking task. And this is a non-inhibitor. And we successfully obtained several candidates with stronger binding affinity compared to that, and all with reasonable structures. This is the synthetic path for our top 1 design. And the same result for the main protease of the SARS-CoV-2. also obtained potential inhibitors with stronger binding affinity compared to a reported one. And to conclude, there are still some limitations. First is the reaction template.
Hi, excuse me. I just have a question for the results. I was wondering if you looked into adding some restrictions to the size of the molecule, for example, or something else that constrains the optimization in some way, because like having worked at these kinds of tasks before, it can happen that the policy, especially for baselines like MultiQN, can exploit the oracle in some way by consistently adding some atoms that will end up giving a higher score. And this, like as you mentioned, is not necessarily desirable. So I was just wondering if you added some constraints like that.
You mean in my baseline comparison or in my method?
Well, in any task or method, like if you imposed like a size limit on the results or something like that.
I see. So for a baseline comparison, I'm just using their recommended setting from the original repo. And and in my methods, I think the constraint is just the synthesizability. So itself, I think, is a constraint.
Okay. Yeah. Thanks.
Yeah. So basically, yeah, it happens that all of the de novo algorithms tend to explore the optimum of the landscape of the property, a surrogate oracle especially. And so I think the best way to avoid that is just have a constraint on the synthesizability.
One question.
Yep.
Do your method prefer like molecule with a smaller number of steps to synthesis, or does that? That's not a constraint at all.
Currently, no, but I think it is a potential application of the model that we can add some properties of the synthetic path, like number of paths or what kind of reactions we prefer, or like the greenness, the susceptibility of the reactions into consideration of the optimization objective. Yes. And so currently, there are some limitations. First of all, the reaction templates are not perfect. When we applied reactions to filter the viable building blocks, we find a lot of pretty active and common reactants are not cannot match even one simple reactions. So which means our reactions are not covering enough space of reactions. And so compared to machine learning reaction predictors that are over optimistically, so our reaction currently are too restricted. And we introduced a depth first order in the generation, which leads to a canonical order of the reactant, and that is unphysical. And that is the problem of the DAG, directed acyclic graph type MDP and the tree type MDP problem discussed in a recent paper introduced by Emmanuel Bengio. And binary, we use the binary presence-based fingerprint, and they cannot distinguish the repeating unit. So my example is when we feed into the model with this molecule, it output this one. So the similarity is very high, 0.85, but you can see this is just one unit of this. So the current fingerprint cannot distinguish the repeating units if there are more of them. And overall, the bottleneck is the first reactant selection, which is the task that's given the least information. And the top one accuracy currently is just about 30%. And so conclusion, so we formulate the task of multi-step synthesis planning and synthesizable molecular design as a single shared task of conditional synthetic tree generation. And we formulate the Markov decision process that could model the multi-step convergent synthetic pathway. And so we the model we proposed could capable of rapid bottom-up synthesis planning and constrained molecular optimization that explore the chemical space defined by reaction templates and purchasable starting material. And we demonstrated some initial results on the recovery rate or the drug molecular optimization. So thanks for listening, and thanks the ONR and MPDS for the funding, and thanks my lab members for all of the help.
Thank you so much for the talk. There has been a few questions in the chat that we didn't answer, so we go over them too quickly. I think Jiramet at some point was asking if the generative model are developed that we were compared to are developed in a synthesizably aware fashion. So I think you were talking about the first baseline.
Yeah, no. So the answer I think is no. So oops. So
yep.
those are, so most of the previous methods, they implicitly define the chemical space to navigate, and the way they define that implicitly define the chemical space is just by allowing the valid smell stream or valid chemical graph that constrained by the chemical valence. So all of those algorithms are just generating valid chemistry, valid chemical structures in terms of chemical valence. So either smells or graphs, and most of the previous methods just doing that.
Okay, just to piggyback on that question, and one of the slides at the end, table at the end, showed that the LSTM have a pretty low accessibility as well. So, but if we don't have any of those constraints, can we explain why the accessibility is so low for that kind of method? Yeah, I think is.
Yeah, I mean
yeah, in this slide here. Yeah.
Yeah, that's also surprising to me as well. But I think first of all, I think it does have some pretty good percentage of the synthesizability, even in the first benchmarking study. But it also does pretty worse performance in some of the objective cases. And in this case, first of all, this is just one task, and it also has a pretty low percentage of passing the quality filter. So they are not fully determining the synthesizability, I think. So I still think, so in terms of synthesizability, to explicitly finding a pathway is still the best method. And so both of them, although I quantify it, it's just as an additional evidence to support my conclusion. And for the reason low short-term memory have a relatively low score, I think is that it doesn't. So long short-term memory. This is a long short-term memory with a hill climbing. So at first is a distribution learning that learns the distribution of normal molecules, so in the training data, and then move beyond the training data step by step, iteration by iteration. So if it didn't move too far, then it could learn some normality of the molecule and preserve it during the optimization. I think that's the reason it behaves not bad. Yeah.
Okay, cool. Next question from Emmanuel Nudai. For the graph GA synthesizability, obviously depend on the action space mutation crossover. Have you considered an action space informed by chemical reaction in your benchmark?
Currently, no. And yeah, we also think about molecular genetic algorithms. Genetic algorithms directly working in the space of synthetic tree, because we saw that genetic algorithm has a pretty strong optimization ability. But the problem is, if we change, if we separate those two branches and to cross over with another branch, it cannot guarantee the root molecules. They could react by following a reaction template. And also, if you change one previous reactant, it can also lead to some unfeasible reactions in the later. So yeah, to apply a genetic algorithm while keeping the synthetic tree valid, I think is a more challenging question than simply operating in a molecular structure.
Okay. Yeah, Julian was asking how sensitive is the recovery rate to the reachable case, in the reachable case, to the setting of K for the reactant search. So I guess he was talking about the beam search if you increase in K.
So currently I'm just using K larger than 1 in the first reactant search, because as I mentioned in the last, the first reactant search is the bottleneck currently. If I just keep it at K equal 1 in all of the selection, then the recovery rate is about over 30%. And as I just mentioned, the accuracy of the top line accuracy of searching the first reactant is also about 30%. So yeah, basically the overall performance is bottlenecked by the first reactant selection. So when I enlarge the first reactant search from 1 to 3, it just the recovery increased to 51%. And for the beam search, for enlarging the case in the following steps, Rocio have implemented that version, and she found that the recovery rate it's an early attempt, so it's not a final conclusion, I think. So the recovery rate didn't increase too much, but the rate of cannot complete a tree is decreased.
Okay. Young-Soo is asking, will there be a quantitative measure to compare your work to other methods that consider synthesizability, forbidding ASKCOS and AEDOG?
Yeah, that's a tricky question because all of the synthesizability is indeed defined by the as we have mentioned. So ASKCOS or the quality filters cannot fully describe the synthesizability we want, and so the best way to evaluate synthesizability is to explicitly find the pathway for them, and the validity of the synthetic paths are defined by the available reactions and available building blocks. And in the setting of DOG and in our models, they are different, the use of building blocks and the reactions. But under our own definition, all of the molecules generated by the models are synthesizable. But yeah, if you ask, is there a general comparison between those two? I think it's a little bit hard unless we can eventually synthesize it in the lab, because even a CASP tool also need a definition of the available reactions and actionable reactions and available building blocks. So it also has a different definition of synthesizability.
Okay. hope that answered the question. Next question. Denise is asking, in which step the generative model is the genetic algorithm? In which step of the generative model is the genetic algorithm applied?
Yep. So the generative model here I constructed is just taking the inputs of the target molecule and decode to product, a synthetic tree and a product, right? So I use it as a decoder. So I use the genetic algorithm to optimize the fingerprints. And when we have offsprings, we use the previous model to decode the fingerprints to a synthetic tree and to evaluate, to select them based on the product molecule, property of the product molecule. And we select the top ones to proceed to the next round. And that's how genetic algorithm works. Is that clear?
Yes.
I also have a question. I was wondering if you can say anything about how your method generalizes with respect to the synthesis path length. So I can imagine that the longer the synthesis path, the more difficult it is to.
Yes.
Yeah, of course, the more difficult it is. But do you see any other kind of interesting results in terms of generalizability?
Yeah, of course you're right. In the synthesis planning, the longer it is, the more the less probability to recover it.
Mm-hmm.
And we didn't find interesting result from that. I think the longest, if I remember right, the longest pathway we recovered in those two sets are about 5 steps.
Okay.
And but in the molecular design, it can generate longer paths because it just evaluated by the property at last.
And how did you split your original data set that you generated? How did you split that in kind of the trained test set?
I just random split by the synthetic tree.
Okay. Okay. Would be interesting to see if you split that by path length or some other kind of property of the maybe target molecule, if you see some different results in terms of how it generalizes. Okay. Thanks.
Yeah, that's interesting. Thanks. Yeah.